Good morning. This is the 8th lecture on advanced computer algebra. We have been discussing how to make things faster. In the previous lecture, we talked about the Euclidean algorithm, and in the lecture before that, we talked about evaluation and interpolation. And we have seen how to make these things faster by taking advantage of fast multiplication. The idea there is to shuffle work that you otherwise in the classical algorithms do by hand, step by step, shuffle this into a big computation, and then just be happy that multiplication is fast, and that makes your algorithm faster. Of course, using fast arithmetic and exploiting the speed of multiplication is not the only way of making things faster. You can make things faster also just by understanding the problem better. And an example of this is what I want to show you today. We will talk about square-free decomposition as the last example for an algorithm where I assume you have seen in Computer Algebra 1 already how to do this, and I will show you how to do this more quickly. But this time we will do it more quickly, not by exploiting fast multiplication, but just by having a closer look at the problem, and yeah, you will see. At the same time, so this concludes then the second part of the lecture where we discussed how to make things faster. And it also prepares and is somehow a kick-off for the third part of the course where we will discuss polynomial factorization. So square-free decomposition is a preprocessor for polynomial factorization, and so it's a good topic for the transition between the second and the third part of this course. So even though I assume that you have seen already how what this is about, let's briefly recall this. What is the problem? The task is this. You're given a polynomial f, and let's assume that it's monic, and you're supposed to find polynomials that are square-free and pairwise coprime, such that the f can be written as the product that's written here, the product of the powers of the g's. So the g1 is raised to the first power, the g2 to the second power, the g3 to the third, and so on, all the way up to the last of them, which is raised to the mth power. Now the g's are assumed to be square-free. This means that there is no polynomial, no proper polynomial, that means no non-constant polynomial, no polynomial of positive degree, such that its square divides one of the g's. In other words, it means if you think of the factorization of the g's into irreducible factors, then you will see each irreducible factor only once in each of the g's. That means for the g's to be square-free. In addition, the g's are supposed to be coprime, pairwise, so any two g's have nothing in common, and this means that every irreducible factor of one g cannot be at the same time an irreducible factor of one of the other g's. So if you think of this irreducible factors of f, then they can appear only in exactly one of these g's. And then if you look at this equation and you see what this decomposition means, it means that you are separating the irreducible factors of f according to their multiplicities. So the g1 is the product of all the irreducible factors of f that have multiplicity 1, and the g7 is the product of all the irreducible factors of f that have multiplicity 7, and so on. So we will see later how to find irreducible factors when we talk more about polynomial factorization. But now in the square-free decomposition, that's somehow a more easy task where you're not going so deeply into the decomposition of f. You're just separating the factors according to their multiplicity, and you're not requiring the g's to be irreducible. We are just requiring them to be square free. All right. So here is a refreshment for your memory. I've said already what square free means. Square free means that there's no polynomial whose square divides the polynomial. So that's why it's called square free. Of course, the polynomial should not be constant. And then to be square free means, I'm just repeating what I've already said, square free means that all its irreducible factors have multiplicity 1. And this g's here, the tuple of these g's, the ordered tuple of these g's is called the square free decomposition of f. That's what we are going to compute today. There's also what I already said, that the idea of a square free decomposition is that in the ith component of the decomposition you have a polynomial which is the product of all the irreducible factors of f whose multiplicity is I. And we may assume that these g's are monic because we're assuming that the f is monic. If it's not monic, then just take out the leading term and write it as an additional factor in front. So these constant factors are not interesting at the moment, so we may as well assume that the given polynomial is already monic. And then we can assume that each of the g's is monic because the leading coefficient of f is the product of the leading coefficients of these factors. If all of them are 1, then this will match. So we can assume that the g's are monic. Actually, since f is monic, here I was a bit more careful than necessary. If f is monic, we can assume that all the g's are monic. If f is not monic, then we can still assume that all these g's are monic because we can assume that the leading coefficient of g1 is equal to the leading coefficient of f. But let's assume that they are all monic to make it simple and not get distracted by things that are not so important. Another thing that we can assume is that the last polynomial in this list is not 1, it's not a constant, and therefore since it's monic, it's not 1. Because otherwise we can just drop it. If this is 1, then it doesn't contribute anything. It means that there is no irreducible factor of f of multiplicity m, but then there's no need to write this. The things in the middle, there could be some that are 1, that I really want to have them ordered in this way that that I have all the exponents without any gaps up to a certain point, and the last one should really occur, but in the middle there could be gaps, and I will fill them up so that I have possibly some of the g's in the middle being constant, but not the last one, because if the last one is constant, it will make the tuple shorter. And with these assumptions that are without loss of generality, it is clear that square free decomposition is uniquely determined by the input, and okay, so it makes sense to ask for its computation. Another thing is that I will use the notation f bar to denote the square free part of f. And the square free part of f is defined as the product of all the g's that appear in the square free decomposition. So that's a polynomial. You can say it's a polynomial that has exactly the same roots as f, just where all multiplicities have been replaced by 1. Whatever they were before, the exponents are turned to 1, and then this f bar is called the square free part of f. So here's a picture. This triangle is supposed to represent the polynomial f. It consists of several factors. There's a factor g with multiplicity 1, factor g2 with multiplicity 2, that's shown here by the 2 boxes stacked on top of each other, and here there's a tower of 3 and a tower of height 4, and so on. So they have different sizes because the g's may have different degrees, and to say it again, they don't need to be irreducible, so the g's can also consist of several factors. There is an issue with characteristic that we'll have to discuss later in this lecture, but to start with the easy case, let's assume that K contains Q, or in other words, that K has characteristic 0, which means that if you take a sum of the several copies of the one element, then you will not get 0 in K for all n in n, except of course if you take 0 once, then this is 0. So it should be n without 0. Now let's see how we can get some information about the components of the square-free decomposition. Let's start with the square-free polynomial g, and we are not going to factor it, but we can think of its factorization. We can reason about the factorization. We can use the factorization in proofs and in derivations, even if we don't have any access to it during the computation. So let's look at the factorization of a square-free polynomial into irreducible factors. So let's call these irreducible factors P1 up to Pm. And since G is square-free, none of them are equal. So they are pairwise distinct and monic and irreducible, these P's, and their product is the G. Now what happens if you differentiate the G? We are working in an arbitrary field, but we have done this before when we talked about interpolation. We see you can multiply, you can differentiate polynomials even without using any calculus. It's just a formal derivation, and the formal derivation satisfies the same rules for differentiation that you are used from calculus, that you are used to from calculus. The derivative of G here is the derivative of this product, so you apply the product rule where you have m factors, so the result is sum of m things, where each thing is a product that is obtained from this product by replacing one of the p's by its derivative. So this sum runs from 1 to m, and in the nth summand, the ith p is replaced by its derivative, so you get pi prime times the product of all the other p's. So here j is the running variable, and it runs over all the p's except for the ith p, which is replaced by its derivative. So under which circumstances can one of the p's be contained in the g prime as a factor? So pi for a certain I is a divisor of g prime if and only if it is a divisor of this expression, because this expression is the g prime. And this expression is a sum of several of summands that include these products, and most of these products will contain the pi. So the pi will divide the whole sum if and only if it divides the sum in which I remove all the products that contain the pi, because that means I'm just adding or subtracting a multiple of pi, and that doesn't change anything about this divisibility problem. But there's just one product which does not contain the pi, and that's the one where the pi is excluded in this product. So this is exactly the case if pi divides this product. This is just one single sum that determines the whole divisibility, because in all other products the pi is explicitly part of the product. So whether I include it or not doesn't make any difference for this divisibility. But now we can simplify this further and say that the pi does not divide any of the pj's that are where the j is different from I, because we said that the p's are pairwise distinct and monic and irreducible, so they have nothing in common, the p's for different indices. So I can drop this product and find that the pi divides its own derivative. Now that's something that's very unlikely to happen, because the derivative has a smaller degree than the p itself, so this is always false. But that means this is always false, and this means that anything that divides the g cannot also divide the g prime. So that means that if G is square free, then the GCD of G and G prime is 1. G and G prime are coprime. And this also works in the other direction, and there it's actually easier to see this because we don't need to mess around with sums and products. We can write that more compactly. So suppose we have some polynomial G that is not square free. So it means it contains a Q whose square divides G. Well, then what happens to the derivative? The derivative by the product rule is the derivative of P times Q square for a certain P. That is just the rest of the factors of G. May or may not contain Q, but anyhow, if I differentiate it, I get P prime Q square plus 2PQ from the derivative of Q square times Q prime. And then you see that the Q is contained in both summons, so it's contained in the whole thing, and we see that Q divides G prime. Q square divides G, so Q also divides G, because Q divides Q square, so we see Q divides G prime and G, and therefore the GCD is not 1, and we have proved the opposite implication. So we see that the polynomial is square free if and only if the GCD of G and G prime is 1. And now let's go one step further and consider an arbitrary polynomial with square free decomposition as indicated here, and see what happens if I differentiate the f. Okay, here I need again the product rule and it's in full generality. And I have to differentiate these powers. The powers are differentiated in the same way as you differentiated powers in analysis. So you get here the sum over all I, and then for each I you differentiate the ith factor in this decomposition, and this is the derivative of it. And then you take the product of all the others according to the product rule. So this is again the product that runs over all j's that are different from I and just copies the factor as it stands in the f originally. And here we see that the current factor, we keep the g, but it has an exponent that is lowered by 1, and in addition we get a factor of gi prime and a factor that amounts to the exponent that comes from the derivation. Okay, so we know, or we see from this formula, that for any k, the gk to the k minus 1 divides the f prime, because it's contained here. If I is equal to k, and it's contained here if the I is not equal to k, because then it's even the gk to the k explicitly written here. So the gk to the k minus 1 is part of each of this summand, and therefore it's part of the sum. However, the next higher power of gk is not part of the f prime, for the same reason for which we saw before, that g prime and g are coprime when g is square free. So if the g, if this was not true, so if this kth power of gk were a factor of g of f prime, then we would be able to conclude from this formula that the gk would have to divide the gk prime. And we saw before that the gk and the gk prime are coprime because the g's are square free. But this means that I can say something about the GCD of f and f prime, because what happens is that the GCD will contain only factors that are factors of f, and they are, well, we have them somehow under control here, but only those that are also factors of f prime, and we see that they are essentially the same things. All the g's that are in f are also in f prime, except that the multiplicity is reduced. So that means that the first one drops out where the multiplicity is 1, so does not survive, but all the others survive. So the multiplicity of 2 becomes 1, the multiplicity of 3 becomes 2, and so on, all the way up to the end. So in this picture that I showed you before, you can think of this GCD, which is very crucial for the computation of a square-free decomposition. This GCD is obtained from the triangle that represents f by dropping the lowest row here. So the G1 disappears and the G2, G3, G4, they have one level less. Instead of 2, it's just 1. Instead of 3, it's 2, and so on. Once you have this, then it's easy to compute a square-free decomposition, and here's the classical algorithm for doing so, which you have probably already seen in an earlier course, but just to refresh the memory, let's go through this again. We have essentially already discussed everything that we need here, and just need to put the pieces together. Input is a polynomial f, and the output is the square-free decomposition. You compute this magic polynomial that was painted in yellow on the previous slide, and if this is 1, then you are done, because that means the f is square-free, and so the square-free decomposition just consists of a single polynomial, the f itself. Okay? Well, let's maybe assume that the f is monic here. Don't worry about this. And if it's not 1, then it means it looks like here, and we recursively compute the square-free decomposition of this u. And the square-free decomposition will consist of all these polynomials, and they will be separated by assumption of the recursion. So the square-free decomposition of this yellow polynomial consists of G2, G3, G4, and possibly more if it continues. So this is what I get back from the recursion. And they are also the components of the square-free decomposition of f, except for the first. But if I know all the others, then I can get the first, because I just have to divide from f the u, while dividing the u out of the f gives me just the square-free part of f. That's not what I want, but I also have the G2, G3, G4, and so on. I can also divide those ones out, and then I get the G1. Okay, so that's what I'm doing here, and then I'm done. So this is obviously correct. It's easy to see that this is correct. I have motivated it sufficiently well, hopefully, to see that it's correct. And it's also not hard to see what the complexity is, because we have to do a GCD computation, and the GCD computation takes m of n log n time, as we discussed in last video, last week's lecture. We've seen that was a very complicated algorithm, but now we are over it, and we can just call it, and we don't see when we use it how complicated it is, and we can just use the complexity that we proved there. But then there's a recursion, and the recursion goes down m steps. So we don't know, or we don't really have a control of how much the f gets faster in a recursive step. It could be that most of the information of f is in the first one, and then the u will be something very small, and then I won't have to do much in the recursion. But it could also be the other extreme, that f is maybe just a power, or an mth power of something, and then all these things would be 1 except for the last. But that means that I won't have a lot of things getting smaller when I go into the recursion. So to be on the safe side, I'm just multiplying here the cost of this GCD by the number of recursive calls that I possibly have to do in the algorithm. And that's something that I don't know in advance, the m. It's part of the output, but of course it's determined by the f. So the algorithm uses m, the length of the output, times multiplication time of n. N, of course, is the degree of f, times log n operations in K. And we are not satisfied with this because we are interested in algorithms that are fast, and this is not fast. What disturbs me here is this m, because so the goal is to eliminate the m. We want an algorithm that just takes this complexity where the m is removed. Such an algorithm we could consider like the previous algorithms where we also had this complexity. We can consider as optimal, or at least almost optimal, because this is essentially linear. So this m of n for fast multiplication time is n times logarithmic factors. But if you allow me to remove or ignore the logarithmic factors, then this is linear. And so this means the computation time is essentially just as much as the size of the input. And there's no hope that we could get any better. So you can hope that you maybe can eliminate the logs or so, but if we don't care about logs, then this is the best that we can achieve. Okay, but this is then now the task that we will focus on now. How can we get rid of this m? And here's a theorem that will help us to do so. So let's introduce some notations. We will take some square-free polynomials. Let's assume that they are monic and pairwise co-prime, so they have no factors in common, and each irreducible factor of g appears of any of the g's appears only with multiplicity 1. I will call g the product of these g's, and this is still a square-free polynomial because the g's are supposed to be pairwise co-prime, so that's a square-free polynomial. And let's take some elements of the ground field, k, maybe 0, but maybe also some other elements. And let's consider this quantity, this polynomial h, which is defined as a sum over this expression here. So you see this one here is a bit similar to what we had here, this product here. If you combine this product with this factor, then you can also write it as f divided by gi, because this minus 1 would be the divided by gi, but if you move this gi to the I into the product without the minus 1, then this would be exactly f, but I'm dividing out the gi. So what this is here, is the expression from before just applied to this g instead of f. Okay, so this is a quantity. So you can say that the h is more or less is a generalization of the derivative. It would be the derivative if the ci is equal to I, but the ci may be anything for this theorem. Okay. And let's also take another constant. And then the theorem says this. I can pick out from this h all the components where the ci is equal to c. And by using this formula, taking the GCD with g and h minus c times g prime. Okay, this one. The claim is that this is equal to the product of all the g's that appear in this product that makes up the g, but not really all, but only all those for which the cj is equal to this c. So it extracts some of these g's, and namely exactly those where this c matches this c. Okay. So it's a little bit hard to illustrate this with a picture, and I've tried to do this. I'm not sure if it's helpful, but let's have a look. You can think of a polynomial always as the root of a polynomial. So let's think for simplicity that all these g's are just x minus something, and let's depict them by their unique root. So here are the roots of the g's, and each g has just one root in this picture. And the root is drawn with respect to x, the polynomial variable. And now the C here, I view this as a, a, a function. So I put a different direction in this coordinate system in the direction of C. And now these roots, well, they are here on a they become vertical lines because they don't depend on the C, and the C does not depend on the roots, and the roots don't depend on the C, so they are vertical lines everywhere. Here you have points where the x component is the root of the corresponding g. And now look at this expression here. So if you look at this expression and you are asking under which, for which c's does this have a common root with this, and then you can ask when is this expression 0, and solve this expression for c, and write c is equal to h divided by g prime, and then you have a function c, so you view c as a function in x. So okay, that's the next step. You view c as a function in x, and then you are asking where does the graph of this function hit certain prescribed values, which are these c's. These c's could be all potentially pairwise different, but they don't have to be. So here, to make the picture a bit more simple, I've chosen 6 c's, but 3 of them are equal here, and these 3 of them are also equal, so they are just 2 distinct c's. And now the function that I already explained will appear in green. This is the function h divided by g prime, and you see this function will hit the blue line at 1, 2, and 3 here, because it's 1, 2, and 3. It will match this, and here it will intersect the other blue line here, here, and here. And this is what this GCD expresses. It says that the product is the product of all those G's where the corresponding C in this linear combination matches the prescribed C. Oh, no, where this C matches the prescribed C. Okay, so that's an attempt to illustrate this theorem. Maybe not. Yeah, I don't know if it was helpful or not. In any case, of course, this is not a proof of anything. Let's prove this, and maybe that will also help to make this a bit clearer. So here's a proof. Proof. Okay, so let's see what the G prime is. The G prime is the sum I from 1 to m, I times G I prime by Gi times G, because the G is the product of Gi I from 1 to m. So this one is the product of all j different from I, Gj. And I wrote before I, but I then deleted it, because the G is really just the product of the GIs with always multiplicity 1. And I have to put here an I if it was a general square-free decomposition of an arbitrary polynomial. That's not the case here. The G is square-free. Okay, and then let's look what I have if I take this quantity that appears in the GCD, h minus c times g prime. Now the h was also something like this, except that it had these additional coefficients here. So it had, so we had I from 1 to m, c I times this gi prime gi g, and then minus from here c times this. So here's a 1. So the 1 gets multiplied by c, so I have this. And now let's see under which circumstances I can have a common factor. So for which j can we have Gj divides this h minus c g prime. Naja, we have a similar reasoning like before. The gj divides, if the gj divides the h minus cg prime, then for this divisibility it is unimportant. Yeah, it is not essential to keep all the factors, or all the summons where gj appears in this g and is not divided out. So this is the case if and only if the gj divides the cj minus c times yeah, okay. cj minus dj prime over gj g. Okay, but now let's make this again explicit. So this thing here is cj minus c g prime times the product of all I different from j. Sorry, I've exchanged I and j now, but I'm sure it doesn't cause too much confusion. So gi for all for all j. And now consider this polynomial. How can it have a factor? So it can have it cannot have anything in common with this, and it cannot have anything in common with this. So this is equivalent because GCD of Gj and Gj prime is 1, and also GCD of Gj and Gi is 1. So this is the case if and only if Gj divides Cj minus C, because it can't have anything in common with this, and it can't have anything in common with any of those. This is the assumption that the g's are square free, and this is the assumption that the g's are pairwise coprime. Now, but this is a constant here. This is a constant, and this is a polynomial. So under which circumstances can a polynomial divide a constant? Can only be the case if either this is also a constant or if this is 0. So if you assume that the gj is not, if this is not 1, then this is only the case if the cj is equal to c. Oh, okay, but that's essentially the proof, because therefore a gj divides this gcd of g and h minus c g prime if and only if the cj is equal to c. So and the claim follows. Okay. So let's see how we can use this theorem. Now we just proved it, but now let's do something with it. We will define now two sequences of polynomials, the v's and the w's, and these are things that I don't know in advance, but let's define them anyway. So given in the end is only the f, and the f has a certain square-free decomposition that I want to compute, but I don't know yet. But even if I don't know, even though I don't know it, I can still define something in terms of the g's. And I define for every k the vk as the product of all the g's starting from the kth g all the way up to the last one. And for the w, I will take a sum that is similar to the sum that appears in the theorem that we just proved, but it's applied to vk, but the vk is also a product of g's. It just doesn't start with 0 or with 1, it starts with k. Also this sum starts with k, so that's fine. And here's a certain choice of c's, and that's exactly the expression that matches the expression of the theorem if you think of the vk as a g for a specific choice of g's. Okay, so why do I define it like this? Here's the reason. If you look at the derivative of one of these v's, then it's again this formula that we have seen a couple of times already now. And so by the theorem that we just proved, we get that the GCD of the vk and the wk minus vk prime is gk. Why is this? Because the theorem says that this GCD picks out the product of all the g's for which the Cj is equal to the coefficient that is written here. Now here there is an invisible 1. So we have to look at all those where here this becomes 1, but this becomes 1, they're all distinct. So this becomes 1 only for I is equal to k, because then you have k minus k plus 1. So then this is 1. So that means you get exactly the gk. So you get the product of all the g's for which this one is 1, but that's only once the case, and it's exactly this one. Okay, that's good, because that means if I have the v's and the w's, then I can get the k's directly. Not like in the previous algorithms where I get somehow a combination of the g's and have to apply recursion to split them further. Here I get them in one shot. But I need the v's and the w's. So let's see how we get the v's and the w's. Now, okay, if I have one v, let me say if I have the w's, then the v's are easy, because with the w and the v I can get the g, and if I divide the gk from the vk, I get the next vk. So I can get one vk from the previous one if I also know how to get the w. But let's see how to get the w. So okay, to get the w, I use this formula here. Wk minus vk prime divided by gk. We just saw that the gk is a factor of this, so I can divide this and still get a polynomial. And let's see what polynomial this is. Yeah, well, it's exactly this here. There is the minus vk prime subtracts from this cj or ci a minus 1 here. So it's this one comes from here, and this one comes from here, and here I have this factor divided by this one. This comes from here. Okay. Now you can simplify this and say I let the k run from one index later, because for I equals to k you get 0 here. You get k minus k, and 1 minus 1, that's 0. So let's start let's have the sum starting one step later, and then you can rearrange here and say this minus 1 here becomes a plus 1 in this minus, okay, and this plus 1 is the plus 1 here. And here you can also say what I also already said before, the vk divided by the gk is the vk plus 1. So what we have shown is that this expression here is exactly the next w. Oh, this is clever, because that means we can get the v's and the w's both one after the other in an iteration. Okay, so this is the motivation of the following algorithm. This is called Yoon's algorithm for square-free decomposition. Here's how it works. It takes a polynomial of degree n and it returns the square-free decomposition. Or maybe we want to assume again that the f is monic. maybe not. Anyway, let's not bother about these details. We compute the u. So remember, the u had the same factors of f, just with all multiplicities reduced by 1. And if I divide the f by the u, I get the square free part, which is the product of all the g's. The product of all the g's is the first v. Okay. The first w is also easy to obtain because that's the f prime divided by u. You see this from here. If the k is equal to 1, then it cancels with this 1, and the sum starts from 1. And then you have exactly here the square free part. The v1 is the square free part. So you have exactly here the formula for the derivative of f, except that all the multiplicities are removed. So that means you're dividing by u. So that's how we get the first v. And we have seen before how we get from one v and w to the next v and w. And along the way, we get also the g's. Okay? So this is just the formulas from the previous slide. We have a GCD computation, and we have here the formula for the w and the formula for the v. And this runs from 1 until m, but I don't know m. Nevertheless, I know that I will finish eventually because I'm always taking out the g's part of the square free decomposition, and the square free decomposition is certainly finite. So after a finite number of steps, this v will not contain any further factors, and then I know that I'm done. Okay, so once this is once this is 1, I know that all factors have been found, and then I stop. Okay, so this is correct, and it's fast. We have succeeded in eliminating the factor of m that disturbed us in the first algorithm. In fact, this is again an algorithm that is the fastest algorithm for this task that is known. Here, as I said in the beginning, here we achieved a speed up without using fast multiplication. So this algorithm also is faster than the first algorithm if you use classical multiplication, although there's no reason to use classical multiplication. Okay, but let's see why this is true. It's maybe not entirely obvious, but it's not so hard to check this. Proof. All right, so let me introduce the notation dk for the degree of the gk for all k from 1 to m. And then I know something about the degrees of the v's. Then the degree of the vk is the sum of the degrees. No, so the vk, so remember the vk was the gk times the gm. So here I have the sum I from k to m dk. Okay, and also what I can also say something about the degrees of the w, and I can't really say this exactly, but I can bound it. I know that they are essentially the derivatives of the v's up to factors that appear in the sum, but the factors have no influence on the degree. So this is bounded by the degree of vk minus 1, so it's certainly smaller than the degree of the vk. So this is the bigger one, and we should focus on this. And then what is the complexity? So the Tn is okay. So what is the work that I have to do? I have to do a GCD computation here, and another GCD computation here inside the loop. So this is the dangerous thing. Here is where we might be worried that something goes wrong. because we might have to do this GCD computation too often. But the v's are getting smaller, and that's what's going to save us. So here we are spending the time of a GCD computation whose runtime is determined by the size of the vk, and then the GCD computation dominates the cost of all the computations that take place in the body of this loop. This is just addition and the division, and so that's all multiplication time. But this one is multiplication time times log n. So let's only take this GCD into account. So altogether we have an O of m of n log n for line 1 plus, and then I have the sum k from 1 to m. I'm finished after m iterations. Even though I don't know what the m is, but still the complexity is somehow determined by how long the loop continues, and it will be m iterations. But in each iteration I have a computation time of O of dvk log dvk. So the log is not problematic. We can bound this by n, and it won't mess up the complexity. Here we have to be a bit more careful. We can take the sum into the big O and into the m, and say this is bounded by, so this I can say equal, because the O already contains the estimate, m of n log n from here, plus, and then it's O of m of sum k from 1 to m degree vk, so, times log n. Okay, and now here something is happening. Let's make this more explicit and say this is k from 1 to m, and this is now what was this? This was the sum of the degrees of the g's. Okay, so this is a sum k, oops, not k, I from k to m also, di. Now I want to flip the order of summation. I have to be a bit more careful here because this starts with k, so I always draw a picture, otherwise I get it wrong. So let's say here's k running and here's the I running. They both run from 1 to m, and let's say here's m, and for every one here, for every specific k, the I runs from k to m. So this runs through this the outer sum runs from here to there, and for every index of the outer sum, the inner sum runs from here to there. Okay, now if I reverse the order of summation, that means I do the summation instead like this, and then I get sum I from 1 to m, and then sum k from 1 to I. You see this at the picture, di. Oh, but now this di does not depend on k anymore. So here I'm summing over I copies of this. So this one here is really I times di. And then in the outer sum there is the I, sum I from 1 to m, I times di. But now remember what this is. This was the degree of gi. So this whole thing is the degree of gi to the I, because I'm taking this I times. And the sum of this is the degree of the product over all I, gi to the I, and that's exactly f. So this degree is n, and then we are done, because we have shown that this sum here is equal to n, and so all together this is O of m of n log n. Wow, so this is really cool. But we are not yet done. So there's one more thing that we have to discuss. Even though this looks like a final answer, but we have to remember that in the beginning we made an assumption, and the assumption was that k has characteristic 0. And for the rest of today's video, I want to discuss with you how to proceed if a k has positive characteristic, because we will later need this when we discuss polynomial factorization. We will always go into a finite field first. And so we should discuss how to do square-free decomposition also in a finite field, and the finite field always has positive characteristic. So the algorithms that both algorithms that I showed you will not work in positive characteristic. But let's see why not, and why they break down, and what of the discussion and the theory that we developed will still carry over to positive characteristic. One thing that remains true is this equivalence. It is also true in positive characteristic that a polynomial is square-free if and only if it's co-prime with its derivative. And for a polynomial, an arbitrary polynomial, square-free or not, with an arbitrary square-free decomposition, it is still true that this product of these components with all the multiplicities reduced by 1 is contained as a factor in the GCD of f and f prime. So remember, in the case of characteristic 0, this GCD is equal to this product. That's what we called U in the algorithms. But now it's still true that this divides the GCD, but in general it contains additional factors. So it doesn't need to be equal, and here's an example. The example is, take the field with 3 elements and take x plus 1 to the 3, so that's certainly not square-free. So if you differentiate this, then something funny happens. The derivative of this is 0, because if you differentiate this, you get 3 times the inner thing times the inner derivative, but the inner derivative is 1. So you get 3 times this, but 3 is 0 in this field, so 3 times something is 0. But that means that f prime is 0, and then the GCD of f and f prime is just f. So we see that the unlike in the case of characteristic 0, where here the multiplicity would decrease by 1, it just stays exactly the same. Okay, so that's a thing that we have to deal with. And in some sense, this example is the only counterexample. That's the only thing that can go wrong, and that's what this theorem says. The derivative of a polynomial can be 0 if and only if the polynomial is a pth power of another polynomial, where p is the characteristic, or even here the size of the field. So let's see why this is true. That's easy to show. It's just a little calculation. So the proof here is okay. So it's an equivalence. So let's go 2 ways. First, this is easy. So if you have no, let's do the easy direction first. If f is a polynomial, is a pth power of a polynomial, then the derivative of it is p times g to the p minus 1 times g prime, and that's 0 because p is 0. Okay, so that's easy. The other direction is a bit longer but not harder. Here you say f prime. What is this? F is an arbitrary polynomial, so let's write down an arbitrary polynomial, f0 plus f1x plus f2x squared plus prime. So what happens if you differentiate it? You get f1 plus 2 f 2x plus 3x squared plus plus plus. And how can this be 0? So the assumption is that this is 0. This is the if part, that this is 0. Now this is 0 if and only if all the coefficients are 0. So this is 0 if and only if if and only if for all I times f I is equal to 0. So this means that for all I, either fi is 0 or I is 0. So in other words, fi is equal to 0 unless, perhaps, if if p divides I. So this means that the f was not as general as I expected here. It has really the form, the following form. It has the form f0 plus fp x to the p plus f2p x to the 2p plus and so on, and up to a certain finite length. Oh, but this means it's a polynomial of x to the p, a certain polynomial g substituted with x replaced by x to the p. But in characteristic p, you can pull out this exponentiation, and that's the answer. So this, the g, you can write down the g. The g is the same as here, but with lower exponents, fpx plus f2p x squared plus and so on. So this is the argument. And okay, now that we understand this, let's see what happens if we still apply Yoon's algorithm. So let's have a closer look at the derivative again. So let's just single out one multiplicity. Let's say v contains all the factors of multiplicity m, and u contains all the other factors. And now if we take the derivative of m, then we can easily write this down by the product rule. It's this one, and this is equal to v to the m u prime if the m is 0. And otherwise, if the m is not 0, well, then we have the same argument as before. If the u is co-prime with the v and the v is square free, then this has nothing in common with the v. So in this case, the multiplicity gets reduced. So for all the m's that are not equal to 0 mod p, the multiplicity gets reduced, and for all other m's, for those that are multiples of p, the multiplicity stays the same. So it's not completely arbitrary what is happening. It's actually just slightly more complicated than before, where we always were in this case. Okay, so this means for an arbitrary f with an arbitrary square-free decomposition, sorry, there's an exponent missing here, this should be gm to the m, so this should be a square-free decomposition. If we now compute this polynomial that was so helpful in the first part of the lecture, we can still explicitly write down what it is. It's the same thing as before, times some correction, and the correction comes from the modulus. So all the multiplicities are decreased by 1, except for those g's where the index is a multiple of p, or where it just stays the same. So if I write it down like here, where everything is decreased, and I'm multiplying those where it shouldn't be decreased back, and that's it. Okay, and with this knowledge, we can now go through Yoon's algorithm and see what it does. It will still compute something, And let's compute what it let's consider what it is. So we have just argued that here in this GCD we get extra factors that correspond to the G's where the index is a multiple of P. So this U is a little bit more than what it was before. That means if I divide this out, that the V is a little bit less than it was before, and the W as well. This removes all the things, all the G's, where it removes all the multiplicities that are equal to 0 mod P, and for the other ones it just keeps a multiplicity of 1 in the V. Okay, and then here the V is still the W is still defined as it used to be defined by this formula, but before these coefficients were integers, and now they are finite field elements. So some of these things can be 0, and then the theorem that we applied before for this GCD, it will pick out more of these things, and not just the one, but also all the other ones that have a distance that is a multiple of P in the index. So this GCD, this G here, will not just be the product of all the irreducible factors of multiplicity G, but it will catch, in fact, all the irreducible factors whose multiplicity is equal to K mod P. So this G is also more than it used to be, and we are dividing this out, and otherwise nothing goes wrong. I will remove here. I will return a certain tuple, and we can say what this is. So it's not the square-free decomposition, but it's a tuple of the G's, where every G contains all the irreducible factor that appear in F with a certain multiplicity, but the multiplicity is taken mod P. Okay, so here's what it looks. We don't get the square-free decomposition of F. If this is the square-free decomposition of F, then what Yoon's algorithm returns is a tuple of polynomials, where the first polynomial is the product of all the G's whose index is equal to 1 mod P, and the second where it's equal to 2 mod P, and so on. And if the P is very large, then this is good enough. So if the M is smaller than the P, well, then there's not, these things don't exist, and you will get the H's are equal to the G. But maybe that's not the case. Maybe we have a small P, and then we'll have to do some post-processing to separate this further. So how can we do this? So let's see. If we have Yoon's algorithm, we have the H's, and we also have the F, because the F was input. And so we can compute this fraction, and let's see what this fraction is. This fraction here, I divide F by these H's as if they were the components of the square-free decomposition. If they were, then this would be 1, but let's see what they are in the general case. So in the general case, the F is this. It has this square-free decomposition. And the H1 and the H2 and so on, they are what is written here. So I plug them in here. And now I reorder them. Here I'm going in steps of P for each equivalence class mod P. But now let's arrange them according to their natural order, so that I can compare them more easily with this one. So what I'm doing here is I have G1, then G2 square, G3 cubed, and so on, up to Gp minus 1 to the p minus 1. And then the Gp is missing. It doesn't appear anywhere. And but then the Gp minus 1 appears again with multiplicity 1, and the Gp plus 2 appears with multiplicity 2, and so on, all the way up to G2p minus 1, which appears with multiplicity p minus 1, and this is how it continues. Okay, so let's write this with a product quantifier. Oh no, let's first write this, see what it does in the exponents. So the indices just walk up all the integers, and the exponents also walk up the integers, but they get reduced mod p. So we can write it down like this. And then let's write it with a product quantifier. And then let's even simplify it further and put it together. And then see that this here is p times the quotient. And you can take out the p and see that this is a polynomial that I can compute. I don't have access to the g's at this point if I have this, but I have the fact that this quotient of polynomials is a power of p. I can compute this quotient of polynomials, and then I can also take the pth root in the polynomials over the finite field with p elements. That's an easy thing to do. We just did this in the proof. And then I can recursively compute the square-free decomposition of this one. Okay, so if I have the square-free decomposition of this polynomial here in the brackets, and I will get this by recursively applying the algorithm, then from the s's that constitute the square-free decomposition of this product and the h's, I can recover the g's. And this is how this works. So the h's are this product, and the s's, if you think about this, maybe that's not sufficiently motivated here, but if you look at this formula here with the quotient, then you can rewrite it so that the j's s is the product of all the i's of the gi plus jp. Okay, and here is the product of the ith h is the product of all j's of GIP. So that means if you think of the g's as being arranged in such a rectangular structure, then the h's are products that are taken along the columns of this arrays, and the s's are products taken along the rows. So if I have the h's and the s's, then I can get all the g's by taking a GCD of one of the s's and one of the h's. And that works at least for the inner part of this grid, because the outer ones, these ones on the first row and the last row, I can't catch because I don't have an H0 and I don't have an S0. I have them only starting from 1. But that's also okay, because if I have the H4 and I can compute all the components of it except for the first, well, then I can just divide all these known components out of the H, and then I will get the first. And similarly for the S. And so we have solved the problem. So we have the following algorithm that solves the square-free decomposition problem in positive characteristic. Here's again just the summary of what I've already explained, just to put it together and record it as algorithm. So f is a polynomial over a finite field with p elements, and this is the input, and I compute as output the square-free decomposition of this polynomial. And to do so, I first call Yoon's algorithm, and I obtain not the square-free decomposition, but I obtain the h polynomials. Maybe I obtain fewer than p polynomials. In this case, I will pad these polynomials with ones, so that I get p minus 1 polynomials. Okay, I won't have to go through this. So in an actual implementation, I would first have a check for a special case, the special case that the degree of f is less than p, and in this case this is just the result and I'm done. But let's assume that the degree of f is large compared to p, and in this case I have to do what this algorithm does. So I get these h's. Now I compute this polynomial that I had on the previous slide, no, 2 slides ago, this one, this polynomial b, which is obtained by taking out of the f this product of the powers of the h's. Then there are two possibilities. Either the b is 1. If the b is 1, then I know that I'm done, because then I know that here all the multiplicities were correct. Then this is already the square-free decomposition, and I don't have to worry about this one because there's nothing left. I don't have to separate anything here. These ones are equal to these ones, and those ones are no longer there. So this is the termination condition for this algorithm. If b is equal to 1, then this is already the square-free decomposition. And otherwise, I apply this algorithm 3 recursively to the pth root of this polynomial b. And this pth root is nothing that I really have to compute. I just have to adjust the exponents. I have to divide all the exponents in this polynomial by p, and this is possible because by construction they all are multiples of p. So this here is a valid polynomial. It's really just an ordinary polynomial, nothing with fractional exponents or so. It's just a polynomial. And the s's here are the components of the square-free decomposition of this polynomial. And now I have to separate the parts using the h's from here and the s's from here. I get the g's by going through all the i's and all the j's. So this means I'm going through that I determine the g's that belong to the inner part of this rectangle. And once this is done and I have these g's, I can get also the g's at the boundary that correspond to 0 times p or 0 plus something by dividing from the h the g's that I have determined in this step. And then I have all the g's and I return them, and then I'm done. So this is the algorithm, and that's also the end of the show for today. Let me say a word on how the story continues. I said already that we have now concluded the second part of the lecture, and we have started already slightly to discuss, to go into the third part of the lecture, which will be about polynomial factorization. We will not directly enter into polynomial factorization in the next video, but in the next video I will discuss another procedure that will also be needed in the context of polynomial factorization, but it's a general purpose technique that you can use also for doing lots of other funny things. And this is the lattice reduction algorithm, the LLL algorithm. Those of you who were in my linear algebra class have seen this already, but I'm not discussing in the linear algebra class how it works, but only what it does. And in the next video I will explain you how and why it works precisely, and we will also recall some of the applications of the LLL algorithm. Is really a lot of fun, this algorithm. And after this we will then enter into the discussion of polynomial factorization, and polynomial factorization is then the topic that will occupy us or keep us busy for the rest of this course. So for today it's enough. Thanks for watching, and see you next time.